Hello, I'm happy to welcome you at our course. This is the first lecture, so we won't get into anything specific. We will talk about what artificial intelligence is, what deep learning is, its history, and modern applications. Okay, let's start. I want to know that this presentation was originally created by Mikhail Butov. This is mostly a translation of the original, which you can find at this link. This is the plan of our lecture. Let's skip it and get to Introduction to Artificial Intelligence. Well, first of all, we want to understand what artificial intelligence is. Generally, it is a field of science which tries to create smart machines which can act intelligently. What do we understand by intelligently? Well, we don't really have any definition for intelligence, and we understand it in a human way. So something intelligent if human requires intelligence to do it and stuff. Okay, overall, why do we need this field? We have two basic reasons. The first is kind of philosophical one, since by creating some artificial intelligence, we can better understand ourselves. If we can create something, we can truly embrace it and understand. And the second one is more of a practical one. It is a wish to get assistant. If we have some intelligent robots, they can do many stuff instead of us and just make our lives easier. The next topic I'd like to talk about is types of artificial intelligence. There are two branches, basically, weak AI and strong AI. Weak AI is a type of algorithm or something like that, which looks intelligent in some specific narrow area. For example, Siri, Alisa, DeepMind, AlphaGo, they're all intelligent. Even AlphaGo have beaten a human at the game, but they are narrow. They don't have cross-domain expertise. They cannot learn new stuff. They're just programmed to do some specific task. On the other hand, strong artificial intelligence is an entirely different thing. And, well, it is hard to explain since we still don't really define intelligence in any way. But great examples of strong AI is robots from Terminator. They are strong artificial intelligence, and well, there are some basic requirements for something to be strong AI. This program has to be at least human intelligent or even more intelligent. It has to be able to learn on its own something entirely new, just like humans. When we encounter some new task, we can learn to do it even if we haven't met anything like this before. And well, we think that it should have self-awareness and consciousness, though we also don't really understand what it is. And luckily or unluckily, strong AI still doesn't exist. When we speak of finding a way to create artificial intelligence, there are many approaches to the task. I would like to focus on two basic ones, which have had the most impact on the development of artificial intelligence. This is artificial neural networks and expert systems. The first one stems from the fact that, well, on the most basic level, our thinking is caused by neurons transmitting some electrical signals. And people who believe in that approach, they say that if we can model this transmission of signals, we can model our intelligence. On the other hand, humans use some symbolic operations when they think. For example, when you try to prove some theorem or do something like this, you operate with symbols. And the second tribe of scientists, they say that we can model human intelligence if we model the way human thinks, if we can somehow embrace and understand how he or she operates on symbols. The first approach is bottom-up, since we go from some biological terms, some neurons and stuff. And the second one is top-down, since it is based on psychological facts and the fact that we operate on symbols. Now let's get to a brief history of development of artificial intelligence. It all started when the first computers appeared approximately in 1944. The person who gave birth to artificial intelligence was Norbert Wiener. He founded cybernetics, which have sparked the studies in the field of artificial intelligence. He also wanted to work with von Neumann, but on this field, but they haven't formed a successful alliance, and it didn't happen. Overall, when the development of artificial intelligence started, these two branches appeared. The first one represented neural networks and connectivistic approach, and the second one represented symbolic approach. Also, symbolic artificial intelligence is usually referred to as artificial intelligence or good old artificial intelligence. The fact is that at the start of development of artificial intelligence, neural networks were not so good, and the leading role in development was taken by symbolic systems. Their rise led to golden years of artificial intelligence, where a lot of studies were carried out. They were pretty successful, and many optimistic people said that in something like 10 or 15 years, everything will be done by robots. However, it didn't happen. Even today, it didn't happen still. So the first AI winter occurred because, well, most of investors were distressed by the fact that the future they were promised didn't happen. The investment decreased, and their studies stopped. However, it wasn't really long since some research from the golden years, they made their way to market and resulted in appearing of expert systems. They were really good in some narrow fields. However, they quickly lost their appeal. Approximately at that time, at 1980s, started the second wave of development of neural networks. It was also a little bit stopped by the second AI winter. However, it also was not really long. And somewhere at 2011, deep learning appeared as a major player in world of artificial intelligence. It was caused by the fact that neural networks scored the highest on ImageNet. It is an annual competition where algorithms compete in ability to classify a lot of images from different classes. Before 2012, it was dominated by algorithms based on something different than neural networks, and after it, neural networks have taken their place and stayed superior to other algorithms just till now. Actually, at 2015, neural networks have got better than humans at this task, and this is what. Okay, so 2012 was the first year, the start of age of deep learning. Now let's get to the question what neural networks are and what deep learning is. Okay, so basically we want to copy a structure of human brain to simulate how it thinks. We can look at neuron. This is the neuron of a lab mouse. You can watch the full video with a demonstration at this link. It has dendrites, which receive signal. It is kind of something like a nose of a neuron, and axon, by which it transmits signals to other neurons who are neighboring it. Dendrites connect to axons of neighboring neurons. And this is the synapse. When dendrite connects with axon of another neuron, it forms a synapse. Actually, each neuron has a lot of dendrites, has a lot of connections to neighboring neurons, and has an axon. We want to model this thing, so this is the model. Okay, how it works. We have many inputs from kind of other neurons, and they are multiplied by some weights which corresponds to a certain synapse. Why do we have this weight? Well, different neurons can have different activations, different concentration of chemical neurotransmitters they send, and this is represented by the input value. However, synapses, they can have different amount of receptors, which also influences the amount of signal our neuron gets from its neighbors. And this number of synapses can be represented by a weight. Actually, you can see the analogy between biological and artificial parts of biological and artificial neurons in this table. However, one neuron is not so strong, and we want to form some kind of network out of it. The most basic network we can form is called feed-forward network. We have input layer, we have output layer, and a certain amount of hidden layers. The input layers can be something like neurons in our eye, which receive light, and output layer is something in our brain which decides whether we see a bird or not, something like this. Such neural networks train data sets using backpropagation. However, in real neural networks in our brain, we can change their structure, and for feed-forward neural network, it stays fixed. And we can only adjust weights corresponding to every connection. Let's look at an algorithm of backpropagation. First of all, we have some input x1 and input x2. And after it passes through the network, we have some output y. First of all, we calculate activation function for the first neuron, for the second, for the third, for the fourth, and so on. Then we get our output, y, and true label z. Okay, so this was the forward pass, which it is usually called this way. Now we want to adjust our weights to minimize the difference, the error between predicted value and the real value. To do this, we calculate an error and propagate it back to every neuron. Why do we do this? We want to adjust weights, and we understand that the higher weight is the bigger impact it has on our error. So in fact, when we go back, when we do back propagation, we kind of redistribute error between every neuron in the previous layer, considering the weights of connections going out of it. We do this for the third layer. We do this for the second layer. And well, actually, now it's time to update our weights. How do we do this? Well, the new weight is equal to old weight plus some learning coefficient, just a small number not to make everything explode, times the error, and times the activation of this neuron. Why do we need an activation? It was input a neuron, so its activation is x1. Well, the heuristic is that even if we have a big weight and thus a big error corresponding to this neuron, it can happen that the neuron from which our connection goes has zero activation, and thus it is not included in error, and we shouldn't update the weight since it didn't do anything at all. Also, there is a derivation of activation function. We needed to understand which way we should update the weight, plus it or minus. We do this for every connection. And we go forward, but actually we didn't really need to go forward, then back, and then forward once again. We could go forward to calculate activations and only once go backward, calculating errors corresponding to each neuron and at the same time updating weights. This algorithm of minimizing an error is called gradient descent, and it's really fascinating since there are so many neural network architectures and they all can be trained using this method. However, we shouldn't trick ourselves and think that neural networks represent what happens in our brain, since there are many important differences. First of all, I'd like to note net topology. Neurons in neural networks are organized in layers when one layer follows another. However, it's entirely different thing in brain. Neurons in brain, they can form some kind of loops, and usually they are organized in interconnected neural centers. And we cannot simulate this structure using neural networks. Also, I'd like to know that in neural networks, the activation from previous layer to the next layer is transported instantly, which is not true for our brain, as different signals from different neurons can come at any time, not necessarily at once, all at once. Also, for neurons, biological neuron can have only two states. It is either fired or not. And our artificial neurons usually have continuous output. And one more important difference is that for neural networks, artificial neural neural networks. We can only simulate, we can only adjust their weights. We cannot change their structure based on some new information. We cannot form new connections, which is really important part of learning, of adjusting to a new task for our brain. There are many more differences, but they're not so relevant to our topic. Okay, so now let's get to what deep learning is. All nets we have seen were pretty shallow. They had 2 hidden layers or 3 hidden layers. However, it turned out that, well, when the neural networks first appeared, they were really shallow because it was too expensive. It was even impossible to train deeper networks. They require a lot more computational power, and there were just not enough data. However, shallow networks, they're not as efficient as the deep ones. They are even slightly worse than other methods, which were used by symbolists, for example. And when we have our humanity have transformed, and we have got access to a lot of data and fast GPUs to train our models, we could make the architecture a lot deeper. As you can see, it is not, this network looks deep, but it's nothing comparing to some examples from recent papers. And such deep networks, they're called, deep learning is called deep since it uses deep networks. Such networks, they allow us to get a lot better results than any other method. Also, to get rid of some buzzwords, I'd like to note that the hierarchy of fields. It's not solidly fixed. However, this terminology is considered to be good most of the times. Artificial intelligence is a field which is generally about thinking machines. Machine learning is specifically focused on building algorithms that can improve themselves through experience, through looking at data. And deep learning is a subfield of machine learning which exploits deep neural networks. Now let's get to applications of deep learning. In modern world, there are 3 main trends in deep learning research. This is computer vision, natural language processing, and decision making. Speaking of every direction, I will tell about an interesting architecture which this field is based on. Now let's talk about convolutional neural networks. They are the main instrument used in computer vision. Convolutional neural networks based on convolutional layers, which use a special mathematical operation which is called convolution. What is convolution? Well, okay, basically we take 2 functions, f and g. We move them relatively once against the other, and we multiply them and look at the area under that curve. We can see that when one function matches another the best, the value of convolution function reaches its maximum. What can we use it for? Well, convolution is really useful if we want to extract, to find some pattern in our image? Well, imagine that we have a big collection of patterns. Then we can take every pattern, slide it through our image, and get our convolution. At parts where the convolution is the biggest, where the value of convolution is the biggest, the matching of our image and our pattern is the best. And using such patterns, we can, collecting such patterns, I would even say building them through gradient descent, we can form convolutional neural networks. This is the simplest example of convolutional network architecture. At the input we have our sign. Then there are some convolutions which transform our image into these feature maps. The output of convolutional operation is called feature map. Then it is transformed once again, flattened. Oh, no, it is another convolution and one more. Then the output of the last convolutional layer is flattened, and we use feed-forward network we have already talked about to make classification. As you can see, it is a speed limit sign with a limit of 60, and it is classified rightly. What can we do with convolution and images? There are many tasks. For example, we can find objects on images and classify them. We can segment our image. What does it mean? Well, find some corresponding class for every pixel of our image. If we have big enough data set labeled with gender, emotion, or age, we can also classify or regress we can classify emotions or find age of a person. Also, we can do more interesting things like style transfer. What do we basically do when we want to transfer style? We take one image, take another image, and generate the third one such that it corresponds to feature maps after convolution for both of these. Not exactly feature maps, but it's specifics. Using the technique, we can combine two pictures. One of them is content picture and another is style picture, and transfer style from style picture to content picture. Well, we get something like this, really beautiful results. Another interesting thing is Lipreading. Using convolutional neural networks, we can generate text which some person says, and well, let's go next. Also, we can generate speech from text. If we have somebody's voice, for example, Barack Obama's voice, we can generate a believable video where he says these things. You can look at this technique in action at this link. Actually, using generative adversarial networks, we can do really fancy stuff like this. For example, what do they do? We can transform an image into some hidden representation, and into some hidden representation as a vector, and do basic arithmetical operations on these vectors. For example, what is shown here? We take some number of images of men in glasses, take their representation, average it, and restore the image, get something like this. Then we take images of men without glasses, average them, and restore their representation. we take images of women and average them. After these actions, we have average man in glasses, average man without glasses, and average woman. Now we can subtract men without glasses from men with glasses. In this case, we get just glasses, and add it to a woman without glasses. After we do this thing, we can once again restore our image and get something like this, woman with glasses. One more interesting result. In recent NVIDIA research paper, they proposed a technique to generate really believable faces of human. For example, look at these two pictures and try to guess which one of them was generated by NVIDIA's algorithm. I bet you won't be able to understand it. Actually, both of them are generated with NVIDIA network. Okay, at that part we talked about computer vision and its main instrument, convolutional neural networks. Now let's get to recurrent neural networks. They let us to work with some sequences, and they're especially useful in natural language processing. As we have seen, feed-forward networks and convolutional neural networks don't have any memory. When we put some X into them, they output something else, and every output is independent. For example, if we put some X1, it outputs H1. If we put another X2, it outputs H2, and H1 and H2, they're completely independent. However, if we work with sequences, we want our neural network to be time-aware, to understand the sequence, and it can be done by transporting the previous, by letting the neural network to look at its state one step ago. What do we do basically? We take output of our recurrent neural network from previous step and add it to a new information. This way, these back connections let our activation circulate inside of a network and give it some kind of memory. However, such simple neural networks, they were proven to be not really good, since their memory is very limited and they forget things really fast. Then Jan Schmidt-Hubert proposed an LSTM cell architecture, which is basically also recurrent neural network, but it has a hidden state which is not directly outputted, it is memory. And every time we want to modify memory, we have to estimate how good our modification is, how much we should forget, and stuff like that. It gives us opportunity to preserve memory for a longer time, not to forget things that fast. Actually, the LSTM architecture is so good that it is used in Google's machine translation system. They use a lot of LSTMs to encode the sentence we want to translate into some hidden representation. And then they once again use a lot of LSTMs to decode this hidden representation into a sentence in another language. Another wonderful result of recurrent neural networks is social bots. An example is Xiaoice. It is a Chinese social bot. It has more than 180 million active users, which is more than the population of Russia. What it can do, it has a lot of skills. One of them is putting a user in good mood. We can see a dialogue here. At first, the system could detect some sense of lostness and sadness in users' messages, and after some talk with Xiao Eyes, it started detecting love and happiness, which is really great. Also, Xiao Eyes can generate rhymed text. It has such an ability, and you can even buy book with verses written by the network. We have discussed recurrent neural networks, which let us work with sequences. And now I'd like to turn to reinforcement learning. This is a universal approach to artificial intelligence. This kind of learning works if we have some agent which can take actions, and each action changes the state of environment which our agent can observe, and success can be measured in some scalar award. Briefly speaking, reinforcement learning takes an agent and tries to find the best agent which can take such actions that they maximize final award. Reinforcement learning is so great that it even appeared at Nature magazine. These are Atari game characters. It was all caused by DeepMind, a startup which was bought by Google for $60 million, who developed a neural network which could play Atari games. All it had on the input are screens from the game. Then they used some convolutional neural network, fully connected neural network, and well, in the end, the network output was an action to take to win the game. This line shows how many games, the games on the left are played by neural network better than the humans, and games on the right are played by humans better. Actually, this is an old table. Now the real border goes somewhere here. I'm not really sure. What do you think are the similarities between these two persons? Well, they were beaten by deep neural networks. Kasparov, who was on the left, was beaten by Deep Blue in chess in 1997. However, the person on the right, he played Go, and he wasn't beaten until recently. What is the reason? Well, for chess, every turn we have somewhere around 35 possible moves, and in Go, this number is on the scale of hundreds. As I remember, around 350 moves on average every turn are possible. Okay, anyway, for chess, the neural network was able to effectively scout this tree to make a tree search and calculate all the outcomes pretty easily, which was impossible for Go, since the branching of this tree is a lot bigger. However, at 2016, DeepMind got to the Nature once again with their network AlphaGo, which could beat the world champion. How did it happen? Well, actually, they used reinforcement learning. At first, they tried to learn from records of games of normal people. Their network learned, but it wasn't really efficient. So they decided to let it play with itself to generate like 1,000 times more data. The network was a lot better after this thing, but still it didn't match the world champions. And they decided to do a little different thing. They tried to use Monte Carlo research with neural networks. For Monte Carlo research, you want to have some kind of weight for every node in your tree to estimate how important it is. They used a neural network to predict this thing, and then they used another neural network to predict the next best move. However, why do we really need this reinforcement learning stuff? The reinforcement learning doesn't only beat games. The same technique can be used in real world. For example, Google used the algorithm from DeepMind to make it control the cooling system of its data centers, and they were able to save up to 40% of costs on this thing. As you can see, when machine learning control was turned on, the amount of electricity spent decreased very highly. Google has a lot of data centers all around the world, and this decrease in spendings on electricity really matters. However, I think that most of this money went on salaries for those who work in DeepMind. Overall, as you can see, deep learning is a really great thing. It changes the world around us. And promises a lot more in the future. I hope to see you on our course. I hope that you will learn a lot of new and interesting stuff. Thanks for your attention.